So let's wait for 1 more minute, and then we shall start. Okay, I think we can start now. So good morning, everyone. So welcome to the class FE 540. So this is the web section, and the course is about the probability theory for financial engineering. So first of all, I will go through the syllabus, and then we shall start the first day lecture. Okay, so my name is Zhenyu Cui. So because we are web section, so I will host Zoom office hour like every Monday, 1 p.m. to 2 p.m. Okay, let me admit one more student. Okay, so I'm going to go through the syllabus here. And for web section, the meeting time will be every Monday, 10 a.m. to 12:30 p.m. And I mean, the course objective, you can read them by yourself. So basically, we are going to learn some basic probability theory. And the main textbook will be this book, which I give a shorthand notation. The FT, I take the first letter of the last name of the two authors. So Dr. Florescu is actually a professor at the Stevens here, and his colleague, like a Tudor, Cyprian Tudor. They have this book. It's called The Handbook of Probability. I think it's a very comprehensive book. And actually here on this side, I'm showing the electronic copy of this book. So the Handbook of Probability, as you can see, just look at the table of contents here. It covers all the topics that we are going to talk about in this course. So I'm going to follow this textbook very closely throughout the lectures. Okay, so let's move back to the syllabus. And there are two more reference books. And this book I call it. So for the assignment materials, actually, I'm going to take some portion from this book. This Ghahramani, like a book, Fundamentals of Probability with Stochastic Processes. So this book has a lot of very good exercises. So I will take some exercises from them, from this book to use as assignment topics. So you don't actually need to purchase this book, I mean this G book, because when I give you assignment, I will just take the excerpt from the textbook. I will just get a PDF, like a few pages of the PDF version of the textbook that shows the assignment questions. So you don't actually need to purchase this book to do the assignment. So still, the main textbook will be this book, FT, like Handbook of Probability. So it's pretty old textbook. You can easily get a very cheap version, like from Amazon, maybe secondhand, or even firsthand. I don't think it's that expensive. So I encourage you, for self-study purposes, to get the copy of this textbook, FT, Handbook of Probability. And these two books, I mean, they are just references. You don't really need to get a copy of them. So if information is needed, I will give you the specific pages from the book. Okay, so let's move on to here about the composition of the grade. So let me make it bigger. So we are going to have about, I think, 5 assignments. So each assignment is about 5% of your final grade. And the attendance is about 5%. And most of the weights of the course are lying in the 2 exams. As you can see, the midterm exam is 30% and the final exam is 40%. So this is the most important. I mean, the assignment and the exams. Okay. So about the tentative schedule. So I list the table here, week by week. So you notice that in the middle part, I tell you like what topics that we are going to cover for each week. And on the right-hand side here, this gives you the corresponding chapters in each of the textbook and the reference book. So you should focus on the FT one. For example, today, after I talk about the syllabus, we are going to cover material related to chapter 1 of the textbook FT. So if you look back at this textbook, you can see that's the chapter 1. It's about the probability space. So today we are going to focus mostly on the probability space. Actually, I will start to talk about the probability measure a little bit, right? Just the beginning page 15, like on the probability measure. But most of the material will be about the chapter 1, the probability space. And then, as you can see, week 2, we are going to talk about these topics, right? These topics in the middle, and the reference will be the chapter 2 in the textbook FT, which is about the probability space, right? And then so on, right? Like week 3, we are going to focus on chapter 3, chapter 4, chapter 5. So you can see pretty much each week we are going to cover the material of one particular chapter in the main textbook FT, right? As you can see here. By the way, on the Canvas, I make some like announcement because next Monday, actually, I will be traveling internationally for a conference. So I mean, we are going to still have the lecture, but the lecture will be replaced by my PhD student, Dongwoo Kim. So I already give him all the access to the Zoom. So, I mean, you still come at this time, like the usual class time at 10 a.m. And then he will give you the lecture. So it's about the week 2 materials. And I'm actually recording all the lectures on the cloud in the Zoom, so you can have access to them after like the class. Also, I'm going to use the whiteboard a lot from the Zoom. And after the class, I will save all the like a handwritten like lecture notes into a PDF and upload to the Canvas so that you can review them and like study them later. Okay, I think this is pretty much about the syllabus. All the other items, I mean, you are certainly welcome to read them, but those are just common sense. I wouldn't spend much time on that. So let me stop here. So any questions so far about the syllabus and the course logistics? Or any other questions? Yes? If you want to ask a question, please ask now. Yeah, if not, then I will just move on to the course materials. So note that, I mean, this course is mostly theoretical, so it's not like the other course. I wouldn't have any slides, right? So what I will do is I will just use the whiteboard to illustrate most of the materials, and I will try to do it slowly because I think you have different backgrounds, right? So I will just try to make sure that you understand each of the concept. Okay, so let me just stop sharing this PDF. Let me go to the whiteboard. Okay, here. Use whiteboard. Classic. Okay. So I think you probably can see this whiteboard here, right? If you don't see it, just raise your hand, right, on the Zoom. I think you can see this whiteboard, so I'm going to use it.
Hello, Professor.
Okay.
Can you hear me?
Yes. Sorry.
Yeah, I just have a question regarding the attendance.
Sure.
Is there like a 5% for attendance? Because I thought for
Yeah,
the
yeah. On the syllabus, I stated 5%. So I think okay, the attendance, I mean, it's I mean, I will just do the attendance probably in the middle of the class, I think. Yeah. I wouldn't do it at the very beginning, so it's okay that you probably attend the class late. In case, I mean, because some of you are working, I mean, in case that you cannot make it for the class, just send me an email in advance so I take notice of that.
Okay.
Okay, so I'm not like a super strict on the attendance because this is web section, right? And you have access to the video and the course material anyway afterwards. So Yeah, don't worry about that. Most of the weights will be on the assignments and exams.
Thank you. Sounds good. Thank you, Doc.
Okay. Okay, so you can see this whiteboard, right? Okay, so I'm going to start writing here. So, okay, hopefully okay, so this is the probability cost, right? FE 540. I will try to write it slowly. Okay, so today we are mostly focused on introducing the concept of probability space. So for some of you who probably already learned about this in the undergrad, that's okay. So we just review it. But some of you may not have learned it before, so that's why I will go slowly. Probability space. Okay. So in order to, so let me give you the answer first, right? So what is a probability space? Probability space has three components: omega, F, and P. So the focus of today's lecture is to explain to you what do we mean by omega, what do we mean by F, what do we mean by P, and give you the proper definitions. So that's the final end product, right? So now we are going to start from the very beginning, so that at the end of the class you are going to understand what is omega, what is the sigma algebra F, and what is the probability measure P. Okay, so let's start with the omega first. Okay, so the omega, so maybe I will just label it here. So this omega is a Greek letter, right? So in the Greek meaning, it means everything, right? Omega, I mean, if you look at the Greek meaning is everything. So actually it's very consistent to what we are going to talk about. So in the probability course, the omega denotes what we call a sample space. Okay, so the sample space, intuitively, let me write it down. So it will contain, so it contains all possible outcomes of a random experiment. Random experiment. Okay, so just take note of this. And because the course probability, so what is a probability, right, by the way? So probability is to study what is the chance of observing a certain outcome when you carry out a random experiment. So the random experiment is at the foundation of the probability, right? So we carry out a random experiment, for example, and let me give you an example. So random experiment can be just you flip a coin. So if you flip a fair coin, there are two possible outcomes, right? One is that the coin will land on the head. One is the coin will land on the tail. So I will use the H to denote the head, T to denote tail. So if I put these two outcomes, I use this curly bracket, I put them into this will be a set, right? So this set has two elements. One is H, one is T. And these are the only possible outcomes, right? Unless, I mean, the coin never landed on one side, right? It's just a spinning, right? I mean, this is hardly possible. I mean, otherwise, there's only two outcomes. So in this case of random experiment, you flip a coin, the sample space omega will be given by this H and T, right? So this is a very simple example. So another example, which I will use a lot, I mean, I use a coin flipping, and the next one is that I will roll a die. Then what is the omega? The possible outcomes. Because the die has 6 sides, right? Each side has a number corresponding to it. So the outcome can be the number 1, number 2, number 3, up to number 6, right? So this is the collection of all the possible outcomes. Okay, so in these two examples, you can understand the sample space. Right? This is what I mean. Now let's make it a little bit more abstract. So let's consider a different class of sample space. For example, if we are counting the number of cars that pass through the George Washington Bridge, right? So the car number cannot be a fraction, right? It can be 0 car, can be 1 car, can be 2 car, and so on, right? So in this case, the omega will be equal to, I use this notation, capital N, to denote the natural integer numbers. So this will be, I put into a set. This will be a set containing elements such that X is a non-negative integer. Let me try to write it stably. Okay, non-negative integer. If you write it out, it will be 0, 1, 2, 3, and so on. Okay, so this is the sample space corresponding to the random experiment of counting the number of cars that pass through the George Washington Bridge. So this is integer. But sometimes we are also interested in the case when we can have a fractional numbers. Like for example, we consider the real numbers, right? So this X will be this R, this is the set I call it R. This will be the collecting all the elements X such that X is a real number. So what is a real number? So real number, you can think of it as all the numbers from minus infinity to infinity. So I use this open like a bracket, right? To denote this is an open set. So it contains all the numbers from minus infinity to infinity. That's what I mean by this notation R. Okay, so this is the sample space. Now, before we continue, I'm going to introduce some mathematical notations. I will just write down some notations that we are going to employ in the later lecture. So, for example, if you see this symbol, right? This is like a capital A, but a flip around, right? So if you see this kind of symbol, it means for any. Right? For example, I can say for any X equal to integer, right? For any X, let me just try to cross it out. So for any X like belongs to integer, blah, 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 right? Some statement like that. Okay, so there's another notation, this E, but I take the image of it, right? Like the mirror image of it. So this notation means there exists. Okay, and then if I have this notation, this is clear to understand, right? This means implies. This is a logical like symbol. Okay. And if I just put the arrow also on the left, right? So you have arrow to the left, arrow to the right. This means the left-hand side implies the right-hand side, and the right-hand side also implies the left-hand side, which means the two sides are equivalent, right? This means equivalent. That's a logical relation. And when we talk about a certain set, if I have this circle, I cross it, this means an empty set. Right? And then I already showed this notation before, but here let's put it formally. So if I say an element omega belongs to a set A, right? This means belongs to. So for example, I know that number 3 belongs to the real number. I also know 1.5 belongs to the real number, right? Because this is not an integer, this is a fraction, but still it belongs to the real number. Okay, so this is the notation. And we are going to also introduce some notation related to a discussion of a set. Any questions so far? If no questions, let's move on to introduce a little bit more notations. So I move on to the second page here. So let's consider there are two sets, right? A and B. So when I say A like this, I use this symbol, right? You can see this is kind of like a, how to say that? It's like a U, right? But you like a turn in a particular position. A belongs to B, right? Like to here. And there's another notation like this, but with not a line underneath it, right? Both of them means subset, right? Subset relationship. So I make it more specific. So A like is a subset of B. This means that A is a subset of B. And this A this belongs to B here without the line underneath. This means A is, so I add an adjective here. It's a proper subset of B. Okay. So you can notice that these two notations, the only difference is that for the second one, I call it the proper subset. So when I say proper subset, so here, this proper means that A is strict.
Yes, I did. I haven't submitted anything yet because I'm still comparing different universities and their programs and offerings.
Oh, okay.
So
are you talking to me? Oh, sorry. Okay. I think let me
it's data science.
Okay. Okay. I just muted one student. Okay. I think he's not talking about our class. Okay. So this problem means that A is a strictly a subset of B. So it will be easier if I use a visualization to show it. So this is a visualization tool that we all often use when we talk about sets. So this is called a Venn diagram. For example, if I have the set A and B, then I can put a circle to denote the set, right? I can put a circle inside the circle, right? For example, the inner circle is called A, the outer circle is called B. Then this is reflecting the situation that A is like a proper subset of B, right? Like in this way. But sometimes, I mean, if A is a subset of B, but A can actually be equal to B, right? So I really cannot draw the equal circle, but let's say A and B are sharing the same circle, right? Then this can be the case that A is a subset of B. So from this definition, we can immediately conclude that the set itself can be a subset of itself, right? Because if the set is equal to itself, it's also counted as a subset, right? That's also possible. Okay. But when we talk about proper subset, we cannot let A to be equal to B, right? Because they are the equal, right? You cannot let it to be equal in the definition of the proper subset. Okay. So this is about the relationship between two sets. Now, let me put it down even more formally here above this line. So A is a subset of B means it's equivalent, right? Remember this notation I just illustrated. If I have two arrows, that means equivalent. It's equivalent to say, what is this notation, right? This notation means for any omega belongs to A, that implies omega belongs to B. Okay, so you can see if we are familiar with all these different symbols, right, notations, we don't need to write down the actual English words, right, for any mathematical statement. We can just use the symbols, right? You can see here, I just use some symbols. I can write down a formal mathematical statement here. Okay, so now I have talked about this omega, talk about this part. So let's move on to the item 3, which is the relationship between the sets. For example, I still assume that we have two sets, A and B. Then I'm going to introduce this operation, A with this cup, right? And then B. This is actually called union. It's a union operation between A and B. So the mathematical definition of the union is such that I have an element omega belongs to the sample space. And then this omega belongs to the set A, or this omega belongs to the set B. Okay, so the keyword is actually this or here. Okay, now if we compare it with another operation, this is A with upside down U, and B, this is the operation called intersection. So what it does is that I consider any elements inside the sample space, and I take if omega belongs to A, I take all the omega not only belongs to A, but also belongs to B. So the keyword here is the and. Okay. And then furthermore, so I have a notation called A with an exponent C here. So this C is the first letter of the word complement. So this operation is called taking a complement. Okay, taking a complement set of the original set A. What it does mathematically is that for any element omega belonging to the sample space, I take all those elements that doesn't belong to A. Okay. And lastly, this is the another operation called the difference. So this is the difference set. Okay. So what it does is the following. For any omega belonging to the sample space, I take the elements that belongs to A and it doesn't belong to B. So technically what I'm doing is I'm going to take A, subtract the B, right? But this subtraction is not understood in the usual algebra way, right? It's understood in the set way, right? So you can think of this difference set as equivalent to the subtraction operation in the algebra, right? But you are dealing with sets. If you take A difference B, that means you take the elements in A, but you exclude the elements that belongs to B. Okay, since we talk about this Venn diagram, it will be very convenient to illustrate all of these four operations using the Venn diagram. So for example, the first one is A union B. So let me draw on the right-hand side. If I have A here, if I have B here, let's say A here, B here. A union B is taking all the elements belongs to A, or the elements belongs to B, right? So this is not a mutually exclusive operation, right? So it can include both sides, which means I have to use a different color here. Oh, here, change the color. Maybe use green. Green is already used. Blue, maybe blue. Okay, so I can do this coloring, right, of A. I can do the coloring of B, right? So you can see I include both of them. So that's the unit, right? So everything in the blue shaded region is A union B. Now let's move on to the A intersect B. So let me draw A here. Let me draw B here. And the A intersection of B, it's very easy. It can be understood as this region where they share with each other, right? Because I say it has to belong to A and has to belong to B, right? So this is quite restricted, right? Which means only this middle portion qualifies, right, to stay in the intersection. And this is actually the intuitive meaning of intersection, right? Because you can see I'm just taking the part where they intersect. Okay, the next one. Okay. Any questions? Okay. Please mute yourself. I will just mute you. Okay. So unless you have a question, you can ask me. Otherwise, please mute yourself. Okay. So the next one is the complement of A. So let me draw it here. So I have to draw the whole region here, right, in order to say about the complement. Because let's say this rectangle denotes omega. A is just inside here. So I will take all the elements that belongs to omega, but doesn't belong to A, which means I'm going to exclude this A here. Let me use a color, the blue one. So I'm going to carefully color all the area outside A, right? But I cannot go inside A. Okay. So all this blue shaded area, this is the complement of A. Now we consider the last one, which is the difference set. So A across B, right? So let me draw A here, draw B here. This is A, this is B. I'm going to take all the elements in A, but I'm going to exclude all the elements belongs to B. So that makes life easier. So I will just take this blue region, but I'm going to exclude this portion, right? Because this middle portion is shared with B. By definition, I should exclude it. So from the Venn diagram, it's very clear to see that we actually have the following relationship, right? So we can do the following implication. So this A difference B operation is equivalent to A intersect the complement of B. This is very easy to understand actually. Let's if I draw the diagram here, you will see it's very easy to understand. So let me draw the omega like this rectangle, that's my omega. So A is A, right? But the B complement, what is that? B complement is all the things outside of B, right? But within omega. Now you take the intersection between A and that area. I mean, you can draw it separately on the diagram. On your take a piece of paper, you can draw it, but you can easily find out it's actually equivalent to this shaded like a blue region. Okay, so just by diagram, we can prove this relationship, right? So this is a visualization way of proving a set like an equivalence result. Okay, so this 1, 2, 3, 4 are basic operations, right? But now we are going to also talk about some non-standard operations.
I just have a question before we move
Okay.
on. First
Yeah,
one,
sure. Yeah,
the A union B,
this one, A union B, right?
shouldn't we also subtract A intersect B from the first relation?
You mean this A union B? We don't subtract. You mean we subtract the middle shared portion?
Middle part, yeah.
We shouldn't do that actually. Yeah, I mean maybe you are talking about this. Because there's later you have a relationship that, for example, A plus B is equal to A union B plus A intersect B, right? This is actually like this is not correct. Okay, sorry. The what I want to see, okay, it's not this inclusion. I'm just saying if A plus B subtract it's A plus B. I think there's a relationship is like A plus B. When you do A plus B, you are actually adding the middle portion twice, and you subtract A intersect B, then you get A union B. Actually, that's correct. Actually, okay, that's correct. Okay, so maybe you are thinking about this relationship, right? Inclusion exclusion relationship. But when we talk about the definition of A union B, we are actually taking everything in.
Yeah, I was thinking of like non-mutually exclusive event.
Okay. Yeah, this is not mutually.
You take the problem.
Yeah, I'm going to only count. So the idea is that I only count the intersection part once, right? So
yeah,
I
so like you take A or B.
Yeah, it's A or B. Yeah, A or B. No matter whether they have intersection or not, it's A or B. Yeah. So another situation, I can draw it here. I can draw it here. Another situation is that they are mutually exclusive, like A and B here, right? Then in this case, A union B will be easy, right? Because you just take everything about A, everything about B, right? That's A union B in this case.
Right.
But here, this is another case when they are not mutually exclusive, right? When they actually share a certain part. Then I basically put a blue shade to everything, right? Here, yeah. So this is the union definition. Yeah. Well, for example, when I talk about A intersect B, in this case, there's indeed an intersection part, right? But if A and B are mutually exclusive, then A intersect B will be empty set, right? There's nothing they share, right?
Right.
Yeah. Yeah, if you draw a diagram, it's very like intuitive to understand all these relationships. So hope that answers your questions.
Yeah, thank you, Professor.
Okay. Then I move on to something a little bit more complicated here. So maybe you haven't seen this in undergrad. So this is let me put on the notation first. This is A delta B. Right? This is taking the so-called symmetric difference. Between two sets. So let me put on the mathematical definitions. It's equivalent to A difference B and then union B difference A. Okay. So this is actually the case I think that when you are thinking about probably. So let me draw it. So here, let me draw the omega. That's the rectangle. I put the A and B who have some intersection. This is A, this is B. Now I use the blue color. So A difference B, union B difference A. So A union A difference B is kind of like this, right? This area. And the B difference A is kind of like this area. So A difference B and B difference A, they are mutually exclusive, right? Because by doing the operation, by definition, right, doing the operation itself actually makes sure these two sets are mutually exclusive. So when I do union, I just put them together side by side, right, add them up. So in the end, this symmetric difference, this A delta B, is reflected by this diagram, right? And you can see I take out the middle part where they actually are, right, like they are sharing, right? Okay. So from this diagram, it's very easy to see the following. So it implies that if I have A union B, difference A intersect B, I will get a symmetric difference of B. Okay. So this relationship can be proved by this Venn diagram, because if I take A union B, I include this sharing like this part, right? But if I difference it, right, I difference this intersection part, I basically means I take it out, then what I end up with is exactly this shape. And this is exactly the asymmetric difference. Okay, so that's why we have this relationship, right? It's proved by this diagram. Okay, so one more thing, if I have A intersect B equal to empty set, then this means that A and B are mutually exclusive. Or I call them disjoint sets. Okay. Okay, that's all we need so far for this set operations. Now I'm going to move on to the next concept. It's called a partition of the sample space. Right? So it's called a partition of sample space. So you can think of it, okay, so if you think about the sample space as a birthday cake, right? So the partition of sample space means I'm going to cut the cake into different pieces so that all the pieces add up to the original birthday cake, right? So I'm not losing anything during the cutting, right? Okay, so in an abstract way, it means the following. So I'm going to look for a collection of sets A1, A2, blah, 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 AN. So it's a finite number of sets, right? Only up to the number n, such that the union between A1, A2, and more union of AN is exactly equal to the sample space. And I want to make sure that AI intersect AJ is equal to the empty set for any I not equal to J. Okay, so let me, oh, wait a minute. Where is it? Oh, here. Now, go back to here. So, okay, let me cross it. Okay, so the partition of the sample space, you can think of it as I'm going to divide this sample space omega into the finite number of subsets, right? A1, A2, and AN, such that all of the subsets add up all together to omega. And furthermore, between two different indices, right? If I not equal to J, right? If you have two different indices, then the two sets labeled by these indices, like AI and AJ, they don't have any intersection, right? Or they are mutually exclusive. So it's just like cutting a cake, right? If you cut a cake, AI is one slice, AJ is one slice, and the two slices actually do not like have mutually, I mean, do not have anything in common, right? The two slices. they are two totally separate slices. Okay. Okay. So this is about a concept of partition of the sample space. So now, since we talk about this set relationship and this one, let us do some simple exercises, right? Let us do some simple examples. Let me put down some examples. Okay, so you are asked to prove the following statement. So I will write down some statements. I will give you the answer, but this is a good way to illustrate the ideas, and probably in some of the homework assignments, you are also going to work on some of them. So let me put down the statement first. Okay, so that's the first statement, right? You are asked to prove that you have two sets, right? The A difference B, you first do that, and then take the complement equals to, you take the complement to A first, and then union of B, okay? So in order to prove this, there are many ways. You can use a fully algebraic way to prove it. That's more rigorous. But for our purposes, we want you to understand the intuition. So it is okay to use a Venn diagram to prove it, right? So the strategy is that you can use the Venn diagram to prove it. So it's very easy. So you draw the Venn diagram for the left-hand side. You draw the Venn diagram for the right-hand side. If the two diagrams look exactly the same, then it's the same, right? So that's very easy. So let's draw the left-hand side first, right? If I have, okay, let me draw this. I need the sample space. That's the Venn diagram for the left-hand side. That's omega. So I have A, I have B here. That's A and B. Now I'm going to use the blue color to illustrate the result. So first I take A, subtract B, right? That means I only keep the parts in A that is not sharing with B, right? This part. And then after that, I'm going to take the complement, right? When I do the complement, I'm going to take all the elements that belongs to omega, but doesn't belong to A. So I'm going to use a different color here. I'm going to use a red color, right, to distinguish. So the complement will be this big area, right? Including this part, right? Because this doesn't belong to A subtract B. Including this part. Okay? So that's the whole red shaded area is exactly the left-hand side. Now, let's start over on the right-hand side for the right-hand side expression. So let me draw the omega here. And I put down the same A, same B here. Okay, what I'm going to do here. So I'm going to take the complement of A. That means this blue area. You have to be careful here, coming of A, so I will just cross here, right? I'm not going to touch inside A, right? That's the complement of A. I'm going to take this union with respect to B, right? So if I take a union, that means I'm going to add back something, right? Because B, you can see most part of B is already inside this A complement, right? Except the intersection part. So when I do the union, I'm going to just add back this missing piece. Actually, in order to, I think that's okay, right? So maybe to be complete, let me just also draw the red one for those blue areas, because I'm taking unions. I'm actually including everything that is already blue will be everything automatically red here, right? Okay, so that's the right-hand side. Now, if you look at the left and the right, just focusing on the red shaded area, you can see exactly the same, right? So that means you can prove this above relationship, right, using some visualization tools. Okay, so this said, let's work out another example, number 2. Okay, let me change the color here. Okay, number 2 is to prove this: A intersect B union C will be equal to A intersect B union A intersect C. Okay, so that's the thing we are going to prove, right? So let me see if I have enough space for that. Okay, let me try. So let's put the omega here. So okay, let's take B union C A intersect. How to draw the most general one? Maybe let's make it all intersection, like most general case. B and C, do they need to be interacting? Okay, maybe let's make life simpler, right? Let's say B and C are mutually exclusive, right? Okay, okay. So this is A, this is B, this is C, and then let's put it down. So B union C intersect with A. Let's do it to the final product, right? We don't need to do it step by step. So B union C, just B add up to C, right? And then you want to take the intersection with A. You can see the intersection are only in this area and in this area, right? That's the left-hand side, right? Now, let's look at the right-hand side. Okay, let's draw the same setup, right? So B and C, they are not sharing with each other, right? But they intersect with A. So this is A, this is B, this is C. Let's take some other things here. So A intersect B, that's exactly this part. A intersect C, that's exactly this part. I'm going to take a union of it, right? They are mutually exclusive, so I just add them up. So you can see left and right, they are the same, right? So this is proof, right? This is also proof. Okay, let's move on to the next page. I mean, so now you can see the logic, right? I mean, if we are not asking for rigorous like mathematical proof, then it's sufficient you just draw the Venn diagram, you can prove everything, right? So what I'm going to do, I'm going to write down the next statement, which is exactly similar, I think, to the previous one. I'm going to skip it and leave to you for exercise, right? So the claim is that A union of B intersect C is equal to A union B. First do that, intersect A union C. Wait, okay? So this is left to you, right? You can draw the diagram and prove it. So let's look at the false statement. So you have A union B complements equal to A complements intersect B complements. So I'm going to illustrate one more case here, right? So let's draw the omega, A and B, A and B, and then I'm going to use the blue color. So I'm going to directly try to plot this, right? A union B, that's the everything here. And the complement is just everything outside this region, right? Okay, that's it, right? Now, the right-hand side. Okay, so use the blue color. So A complement, that's everything outside. Let's draw it. So blue color, maybe I will use in the end I will use blue color, right? But for now, let's use maybe yellow color. So the everything outside C, right? Outside A. Okay, like this. Intersect with everything outside B, right? Everything outside B, let me use another color, maybe purple. Oh, gosh. Okay, everything outside B. Now I'm focusing on the intersection between them, right? So the intersection between the purple and the yellow, as you can see, is exactly this, right? On the left-hand side. I don't have a different color to do it, right? It's too messy. But if you look at the intersection of the yellow shaded region and the purple shaded region, you can observe that's exactly corresponding to the blue region on the left. Okay, so the proof will be done. Okay. Now the fifth statement is that A intersect B complement is equal to A complement union B complement. So this is left to you as exercise. Okay, so these are some examples. Now I'm going back to the lecture, right? So just want to make some observations, and they are the following facts. So there is some facts. So if I take the sample space, I take the complement to the sample space, what is that? If you look at the definition of the complement, that means the set belongs to omega, but it doesn't belong to this set here, right? So if you have a set that belongs to omega and doesn't belong to omega, that means what? That means it's empty set, right? There's nothing that can satisfy this contradictory conditions. So from a dual perspective, the complement of the empty set will be the complete set, right? The sample space omega. And then we also have A union of AC, right? So basically take A and take everything outside of A, add them together, that gives us the whole sample space. That's easy. And similarly, A intersect with AC because they are mutually exclusive, so that's empty set. And then if you do the operation twice, if you do the complement of A and take a complement again, you get A back, right, in its original form. Okay, so these are very easy to understand. These are just some basic facts. Now I'm going to move on to the next concept about the functions. So what do we mean by a function? So we already talked about the set, right? Set is just a collection of elements. A function is actually talking about a mapping between one set to another set. So the function is a mapping from domain to the image, right? So the domain is a set, image is a set. So if I draw it visually, it's like this. You have two sets. One is the domain. One is the image set or the range. Or sometimes people call it the range of the function, right? These two are equivalent. And then I'm going to draw a mapping, and this mapping is F. And notice that this mapping has a certain direction, right? It's from the domain to the image, right? Because the arrow is pointing to the right. So this direction is very important, right? You cannot just take the direction back, right, from image to domain, unless you are talking about what we call the inverse function, right? So I can just put down it for completeness. If you go from the domain to the image, that's the function F. If you go back from the image to the domain, that's what I call F inverse, right? So here, let me say here, F inverse means the inverse function. Okay, so that's a basic concept of a function. Now we are going to move to a very important subject matter to define the probability space. So let's review back like where we start from. So like I say, in the end, you are going to understand this three concepts, right? There's omega, F, and P. Now we have talked about omega. Omega is a set, right, containing everything, right, all possible outcomes. That's why we talk a lot about all the different sets. Now we are going to move on to the second object, sigma algebra, is F, right? So the next subject matter is the sigma algebra. Let's move on to the next page. That's the sigma algebra. So this is something you haven't seen in undergrad, right? You probably have seen a lot of the set operations in undergrad, but sigma algebra usually is for graduate course. Okay, unless you do undergraduate in pure mathematics, you learn about this for sure. Okay, so the purpose, right? The motivation of introducing this sigma algebra, right? So the motivation here is that we need a proper domain to define the probability function, right? We need a proper domain to define the probability function. Okay, wait a minute. Okay. So I mean, we talk about function, right? Function is a mapping between domain and image. Now let's restrict ourselves to a specific function called a probability function, right? It's not just any general function, it's a probability function, which is what we are interested in this course, right? So in order to properly define a probability function, we have to identify the domain and the image. The image is easy actually, right? The image for probability is always 0 and 1, right? Because any probability is between 0 and 1, right? You can have at the most 100% probability of anything. So that's easy to understand. But the domain is a delicate issue. That's why we are going to introduce some basic building blocks in order for us to precisely define what do we mean by the domain of a probability function. And the right building block for the probability function is the sigma algebra. That's why we are going to introduce the sigma algebra. Okay, so this is the motivation of what we are going to do. Now, before we talk about sigma algebra, we have to talk about what do we mean by algebra, right? So there are two things. It's split into two steps. First, we introduce what do we mean by algebra. Then we are going to restrict it to define what do we mean by sigma algebra. Okay, so there are two steps here. So let's talk about maybe the definition of algebra here. So the definition is algebra. I mean, this algebra is different than, for example, what you learn in high school, right? It's not like those algebra, right? So it has the same name, but yeah, it's a different abstract concept. So here, omega. So I assume the sample space omega is non-empty. And I consider a collection, I name it F, collection F of events is called, I divide it stably, called an algebra. That's B, algebra, if and only if and only if, sometimes I use the shorthand notation IFF, okay, to denote if and only if. That means the necessary and sufficient, okay, both directions. If and only if it satisfies the following three conditions. First is that omega is a subset, is an element, sorry. Omega is an element of this F. Second, if A is an element of F, then A complement is also an element of F. Number three condition. If you have two sets, A and B, both are elements of F, then A union B will be also elements of F too. Okay, let me just put it down here. So clearly, this F, so intuitively, so let me write it down clearly. This F is a set of set, right? It's a set of set. So what do I mean? I mean, it's a collection of sets, right? So it's a collection of sets. Or put it another way, set is an element of F, okay? So this algebra is taking the set as its elements. Previously, when we talk about all this different sets, the element, for example, this omega, right? This omega usually are just numbers, right? Just like a real number, just like a integer number, right? They are not set itself. But when we talk about algebra, it's kind of like treating this little omega as a set, right? And then it's an element of the algebra, right? So algebra, in this way, you can think of it as the set constructed on top of a set, right? So that's why I call it a set of set, okay? Here. Okay, so this is a little bit abstract, right? But later we are going to have some coin for the when you roll a die, right? Like I'm going to list what do I mean by the algebra and the sigma algebra over there. Okay, so for now, just bear with me and let's talk about some property of this algebra. So you can see each of these defining property. Let us first give some intuitive explanation, right, for this properties. So the first one, omega belongs to F. That means what? That means first of all, we collect, right? So think about this algebra as a collection of sets, right? So first of all, we collect the sample space first, right? Collect the sample space. And the second one means if set A is an element of my algebra, then the complement is also an element of my algebra. Now, you already know omega is belonging to F, right? That means what? This second one implies omega C belongs to F. Or equivalently, that means empty set also belongs to F. Okay? So just from 1 and 2, right, you conclude that the empty set also is collected into my algebra. Now, the second one, if A and B are elements of my algebra, then A union B is my element of my algebra. So given this first two information, so I can just write down my algebra as a set containing phi and omega, and possibly something else, right? We don't know yet. But at least these two are the basic elements in my set. So clearly, my algebra is not empty, right? So clearly, I can conclude my algebra is not empty, right? This I can conclude. Because at least I can identify two elements, right? One is the omega, one is the empty set. There are two elements here. It's not empty set. But how about if we have more, right? We don't know yet, right? Depends on the actual situation. For now, in this basic setup, I have this two, right? But in some specific applications, for example, if I'm talking about flip a coin, I can add more elements to my algebra. Okay. So in the end, you can think of this algebra as a collection, right? Collection of sets with particular properties. Okay. Now let's develop a little bit more on the property of an algebra. Okay. So I have this following proposition. So this proposition is actually taken from the textbook, right? From the Dr. Florescu textbook, right? The FT textbook. So let me call it the proposition. I mean, my lecture are actually based on that textbook, right? I just try to explain some of the intuition, but for your self-study, it's very important. I mean, after the lecture, you read the textbook, right? For example, chapter 1 of the textbook, and it can give you more details, right? Or a different perspective of the same concept. So it's very important that you actually read the textbook, right? So do not just, okay, my advice is this. I mean, do not just rely on the lecture notes and the lecture, right, to understand the subject matter. So it's very important for you to actually read the textbook and utilize the lecture as a supplement, right, to understand better the concepts in the textbook. But the textbook is very important. Just do not skip it, okay? Now, let's look at these properties. So let F be an algebra defined on this sample space omega, then we have the following properties. The first one I already talked about it, right? The empty set is an element, right? This already talked about it. Now let's look at the second property. If A and B are both elements of the algebra, then A intersect B also elements of the algebra, right? And the number 3 is that for any n belonging to the integer, right? Non-negative integers. We talked about this before, right? So basically this is from 0, 1, 2 up to infinity, right? So if A1, blah, blah, An are elements of F, remember this n is a finite here, right? Then the union I from 1 to n of AI belonging to the algebra. So this is the property. The first one I already proved it, right? But for the second one, I can give a very simple proof here, right? So just by the property, just by the definition of the algebra, if A belongs to F, so let me put down the mathematical notation here. So A is an element of F implies that AC is an element of F, right? B is an element of F implies B complement is an element of F, right? This is very easy to see from this, right? Second property in the definition, right? Sorry, not the property here, right? This is definition from the second item in the definition of the algebra. Now, we also know that if AC is element of F, BC is element of F, altogether, right? This implies what? This implies AC union BC is an element of F, right? Here, right? This is using the third item in the definition of the algebra, right? If A, B belongs to F, then the union belongs to F, right? Here, AC belongs to F, BC belongs to F, so AC union BC belongs to F. Finally, now we use the relationship, right? So now using the relationship that AC union BC and take a column again is equal to A intersect B, we prove it, right? So this relation, I mean, we leave you as exercise, right? Let's look at here, right? Like AC union BC, right? Like here, right? It's equal to, if I put a complement on both hand sides, right? For example, to number 5 here, I get what I mean. Right? You can easily prove it by Venn diagram. So from this fact, we prove it. Why? Because this element, right, belongs to F. Then this element also belongs to F. And the complement is exactly A intersect B. So what? So A intersect B belongs to F. Okay, so this is proof. Similarly, you can continue on and prove this one. It's more complicated, so I wouldn't like prove it here. I mean, I mean, for the assignment and in midterm, I will not ask you to prove something like this, so don't worry about that. Just for your own understanding, right? Okay, so this is the property here. Let's move on. This is algebra, right? So now the second thing, this is just preparation, right? So the final thing we want to get is so-called the sigma algebra, right? So sigma algebra. You can think of it as a generalization of algebra. Okay, it's a generalization. And let's put down the definition. I don't have, I think I have space here. So let me utilize the space here. Okay, so the definition of sigma algebra. So sigma, okay, let me try to write it carefully. Sigma algebra is, first of all, an algebra. And in addition, replace the item 3 in the definition of algebra by the following. I call it a number 3 prime, right? So this is previously is item 3, right? This is item 3 prime. So this is the new condition. So the new condition is such that the union when n belongs to this non-negative integer numbers of an belongs to F, where this n belongs to n is a natural number, which means it's an integer plus the 0, right? It's a natural number. And an is an element of the F for all n. So that's it, right? So you may wonder, like, what exactly is the difference, right? So if you look at the algebra definition here, it means, okay, if A union B belongs to F, right? And one property is like this. For example, if you look at here, right, then the union of AI when I from 1 to n belongs to F. But the key difference, let me use a color to know. The key difference is this. This n, implicitly, we assume is finite. Right? Finite, implicit. But here, look at this. That's the crucial distinction. So here, when we talk about this union, we are not like only considering this union up to a finite number. It actually holds for any like n here, right? For any like no matter how we count it, right? So the thing is, may not be counted like sequentially like 1 to n like this, but actually it's taking into account all the possible ways of counting it, right? So I call this a countable union. Okay. Union. It means we can do like it includes all different ways of counting, right? Counting the indices, right? So for example, you can count it by all the numbers, right? 1, 3, 5, blah blah blah. You can count by all the even numbers, right? Up to infinity even, right? There's no cap here. But here you can see this is only capping it at a finite number, n, right? So I only consider union up to a finite number. But this, another difference I want to say here, there's no cap on the number of unions. Right? You can like take the union up to any number, right? Super huge number. Okay. So this is a countable union. That means what? That means sigma algebra actually requires like more, right? It's even more strict, right? In the sense that I have to make sure not just the union of a finite number of sets belongs to F, but I have to make sure a countable union of the sets AN belongs to F. So this is more restricted, right? Although I say it's a generalization of algebra, but the requirement for you to construct a sigma algebra is more restricted. Okay, so I would say it's more restricted to construct. Okay. Okay, so it's a little bit more, it's a little bit abstract here, right? But us, I mean, we only need to understand it at this conceptual level, right? We do, for example, we don't need to go to the very tough one, right? Called the monotone class theorem, right? Or those kind of complicated ideas. I mean, the definition is exactly what you need to know, actually. So just before that, let's look at some further interpretations. So we have the following like interpretations. So the sigma algebra is closed under countable union. And in comparison, algebra is closed under finite union. Okay, so that's the main distinction. One is countable, one is finite. So if you want to dig further about these two concepts, you can search the keyword countable number and finite number on Wikipedia. Right? You will get a lot of discussion about the theory, right? How the framework of natural numbers, how do we define all these two different numbers. But essentially, what I mean is a countable number is like it can go to infinity, but in a countable way, right? You have to have a particular logic of how to count the number, right? For example, 1, 2, 3, 4, up to infinity, right? For example, 1, 2, 3, up to possible infinity. But finite union means 1, 2, 3, up to a particular n. And then you stop here, right? Stop at a finite number. You don't go on. But for countable number, you can keep going on given that you have a feasible way to actually count each one of the number. Okay, so that's the key difference. Yeah. And certainly, if you go on Wikipedia, you will also see the concept. There's another class of number, right, called uncountable number. Right? Uncountable number. That means those numbers are certainly not rational, right, which you cannot count, right? Because if you look at, if you want to go deeper, there's a rational number, which are those numbers that can be represented as a ratio between two like natural numbers, right? Any rational number, it can be a fraction, but it's okay. It can be expressed as a ratio between two natural numbers. And natural number is countable, right? So this m is countable, this n is countable. So this q is actually also countable, right? Because you have a feasible way of constructing each of its value. Okay, so if you have something that is not rational, then it's uncountable. For example, a typical example will be the pi, right? Pi like 3.14156, blah, 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 right? Continuing Asian. So this is an uncountable number, right? Also the natural E, right? E like a 2. I forget, like 516 or something, right? That's the natural E number. So I call it natural E number. So those numbers are uncountable, okay? So, I mean, this is certainly not the main subject matter of this course. So, I mean, if you're interested, you go to Wikipedia, right? You get more of this. What I want to say is that sigma algebra is more restricted, right? Because I have to assume that the events constructed as a sigma algebra have to be closed under countable union. So what do I mean by closed? Closed means if you have, for example, if you look at the definition here, if you have the set AN belongs to a sigma algebra, then the countable union of it also belongs to sigma algebra. This is what I mean by closed. So intuitively, it means by taking countable union, you don't go beyond sigma algebra. You are still within the class of sigma algebra. That's what I mean by closed. Okay. So think about like you close the boundary, right, of your country, right? Like you don't allow people to get out, right? Basically, that's what I mean by close, right? If you think about sigma algebra as a territory, right, as a country, right, and then any set, right, it's like a resident of this country, right, and then if you do countable union of the set, it doesn't go beyond the boundary of this country, right? That means it's closed, right? Okay, so that's how I interpret this. So now let's look at the next. So why do we need the sigma algebra for? Because remember the purposes, right? The original purposes for us is to find a nice or proper domain to define the probability function. And it turns out that this sigma algebra is a very good domain, right, for defining our function. So let's put out some intuition here. So sigma algebra is what I call a very nice, right? It's a nice collection of sets. Why? Why I say it's nice? Because it's closed under all the possible set operations that we have talked about. Remember, we talked about the set operation called the union, right? Intersection, taking complement, taking the difference, and also combination of them, right? If I combine union with difference, right, I get the so-called symmetric difference. Yeah, so essentially you can see that sigma algebra is really nice, right? And another good thing is that it's closed under all this operations, like these are operations, countable number of times. This countable is particularly important for probability. When we talk about probability, for example, if you flip a coin, right? Let's say you flip a coin until, I mean, infinity, right? You keep on flipping the coin, right? Then what you have is a situation of a countable situation, right? For example, let me put the example. If you flip a coin, let's record down the outcome. First time you get head, second time still head, then you get tail, you get head again, you get tail, blah, 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 and so on, right? So this is an event that is countable for sure, right? Because you can count each one of them, right? And then it's it's countable until, right? So you have a way to count it, and then until the infinity, you can go to infinity, right? So this is a situation that is possible to define a sigma algebra, right, based on this set, okay? Because it is closed on the countable number of operations, okay? So similarly, I mean, we are talking about finance, right? Financial engineering. So the stock price, right? I mean, stock price is very complicated. I cannot just simply do that, but I can at least, for example, if I borrow some idea from maybe construction of binomial tree, which you are going to learn, I mean, later, right? If you learn the FE 621, right, computational finance, you are going to learn this binomial tree. But anyway, if I borrow this idea, the key idea of the binomial tree is that we think the stock price as going up or down, right? So basically, you have S0 here, you have S up, S down, right? So SU is the stock price if you go up, SB is the stock price goes down. Then it's very similar to the flipping a coin situation, right? The stock price can be going to SU, or it can go into SD. Then the next time, if you further go up, it can be SUU, it can be SUD, it can be SDU, it can be SDD, right? And so on. So you have a countable number of possibilities, right, for the evolution of your stock price. Then if I want to study, build a probability theory based on the modeling of the stock prices, then sigma algebra is very natural, okay? So you can see sigma algebra is actually the perfect building block for defining the probability, right, the probability function. Okay. Then just as an extension, since we are talking about this here, later, for example, if you learn the FE 610, FE 621, which are the key courses in the financial engineering master program, you are going to learn the concept of stochastic processes. So intuitively, I mean, you can think about stochastic processes as a random variable indexed by time, right? Later, I mean, the next lecture, we are going to talk about random variables. Actually, my PhD student will talk about it. But essentially, stochastic processes, you can intuitively understand it as a sequence of random variables. And the sequence is indexed by the time variable. Right? Just think about the SP500 index, right? It's indexed by the time, right? Each time you see an observation of the SP500 index, that's a kind of like a random outcome, right? That's a random variable. So if you connect them all together, you have a stochastic process, right? To model the SP500 index. Okay. So in the modeling of the stochastic processes, we are also going to introduce a concept. There's a key concept there. It's called a filtration. So this filtration has very close connection to the sigma algebra that we have talked about. So equivalently, a filtration, you can understand it as increasing sigma algebra indexed by time. So in order to properly define a stochastic process, I need to introduce the domain, right? Basically, this is the domain for the stochastic process, the filtration. And because the stochastic process is a sequence of random variables indexed by time, so naturally, what we are going to do is this. Because the domain for defining a random variable is the sigma algebra. Now, I'm talking about some random variables indexed by time, so it's very natural to extend it to sigma algebras indexed by time. And this is precisely filtration. Okay, so this is very crucial for you to understand stochastic calculus, like all this computational finance stuff. Okay, so I'm just giving you a preview of what you're going to see right soon, and the connection to the sigma algebra that we talk about now. Okay, finally, right? So we have, let's see our task, right? So today's task is very simple. We just need you to understand three things, right? Omega F and the next one, right? So actually we have ticked the omega now, right? We know omega is a sample space, is a set. We know all different operations of omega. Now we know F is a collection of sets, right? That's, we talk about algebra. And for probability purposes, the sigma algebra is more appropriate for F, right? So this F will be a sigma algebra. And let me just recall you, right? Yeah, this is the sample space. And this is the sigma algebra. Now, this one, right? Task 3 is what we are going to do here. It's the probability, right? We have to define the probability function, right? Finally, that's the probability function. So we can fill it in. That's P, right? That's what we are going to introduce. Okay, so let me introduce this first, and then I will give you some examples of sigma algebra. So probability measure, I just have one proper definition. That's actually at the beginning of the chapter 2 in the FT textbook. Okay, that's okay. So I'm just going a little bit advanced, right, to chapter 2, but that's okay. So, okay, so now let me say this. So we have already identified omega F. They prepare us for probability theory. And now we restrict the measure. Okay, sorry for the writing. Write more stably. Yeah, restrict the measure. Okay, to 0 and 1, right? So the image, right, or the range is 0 and 1. And now we formally take the domain to be at the sigma algebra on the omega. So let me just see if I erase this. This is badly written. Okay, let me just put it at the sigma is the symbol. Algebra. Okay, so let's draw the diagram for the mapping. So here, this is F, right? Here, this is 0 to 1, right? So this is the image or the range. It doesn't matter. This is the domain of the mapping. And then I'm going to take an element from the domain and map it to an element in the range. And this mapping is what I call P, right? Of an event, right? So I have to certainly specify an event. That means here I have to take an event A that is an element of the sigma algebra generated from omega. Okay, so the logic sequence is very simple here. So I have omega, I generate a particular F, and then I'm going to utilize this F to define the function, right? To serve as a domain and define the function P, that's the probability function, that can map any element A belonging to the sigma algebra into a value, a particular numerical value within 0 and 1. That's it. That's the purpose of a probability measure. So that we have, let's put it down here, PA belonging to 0 and 1 that implies for any A, which is an element of the same algebra. Okay, so we can formally state something like this. Now we need a formal definition. Right? This is still intuitive. I give you the mapping, like the visualization, but this is still intuitive. Let's go to the formal definition, which is actually the definition given in the textbook, right? The Florescu textbook, chapter 2. So the formal definition. Okay, so we are given a measurable space omega f, a probability measure is a function. So it's a function that is a mapping between f to 0, 1, satisfying the following three, right? Or two, satisfying the following two properties. Okay, satisfying the following two properties. One is that it will assign a value of 1 to omega. So recall that here, omega must be an element of F, right? That's very simple, right? Because by the definition of stigma algebra, omega and empty set, both are elements of F, for sure, right? So for this particular omega, I'm going to assign the value 1, 100%. So intuitively, this means, because omega is the set containing all the possible outcomes, right? So all the possible outcomes corresponds to 100% probability. That's intuitive, right? Okay. Now, the second one is something a little bit artificial, right? That's something we add, right? The first one is very natural, right? That's intuitive. But the second one is something that we add in order to create the probability theory. And it has a name. This is the definition called countable additivity. Countable additivity. Okay, so I'm going to take for any sequence AN, and the sequence is indexed by natural numbers. And it's a sequence of disjoint events. In F, i.e., it means AI and AJ, the intersection is empty set for all I not equal to J. Then we have the following additivity. So the probability you assign to a countable union of the set AN is equal to the countable summation of the individual probabilities. Okay, that's it. So that's the definition of a probability measure. Okay, so yeah, that's it. And then finally, after I introduce this, then omega F is measurable space equipped with the new member. P is formally called the probability space. And with this notation as the triplet, or the omega and P. That's it. So this is the three foundational pillars, right, of a probability theory: sample space, sigma algebra, and the probability function or probability measure. Okay, so that's it. Now we have to describe a little bit the basic properties of a probability measure. So let me start a new page here. So some,
Professor, can we go over the second point one more time, just to...
okay. Yeah, second point, right? Countable additivity, right?
Yeah.
Okay, sure. This means, okay, so this is just the setup, right? So you have a sequence of disjoint events, right? Like here, and then they are all in F, right? So all this AI, AJ are all in F, right? Which means all the AN are in F, which I forgot to say. Yeah, so all AN belongs to F for n running from 1 to blah, 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 right? And so on. So this is a specific property of the probability measure. So this is a mapping such that if you take the countable union of all the sets, you map it to the sum of the individual like probabilities. So put another way, this means the probability measure P is a linear measure. So if you take because taking union is kind of like, because they are disjoint, right? You see this AI, AJ are disjoint. So taking union of them is just like summing all the sets, right? If you sum all the sets, you plug into the, because this countable union is still belongs to F. Remember this n from 1 to infinity of this AN also is element of F, right? Because of that's the property of a sigma algebra. For algebra, this doesn't hold, by the way. For algebra, if you take an n from 1 to infinity, the countable union, it doesn't belong to algebra. For sigma algebra, as I say, it's more specialized, right? So it actually, this will hold, right? It still belongs to a sigma algebra. Okay, so if this is sigma algebra, you can assign this probability to it. Then the probability you assign is equal to the sum of the probability you assign to each individual like events. So maybe let me, just give you a simple example here. Label it here. Let's consider some disjoint events. For example, the simple one is always the flip a coin, right? So let's define the events, right? So A1 is the event that you observe a head in the first flip, right? That's the first flip. So A2 is that you observe a tail in the second flip, right? These two events are certainly disjoint because it doesn't affect each other, right? When you flip a coin the first time, the second time, they don't interact with each other, right? So they are disjoint. Now, you want to assign some probability to it, right? So let's say you take a A1 union A2, right? And then you assign a probability to it. So what is the probability of this, right?
Just add the probability of each event, so 1/2 plus 9.
Yeah, because this is the union, right?
Yeah.
Union, be careful here, this is not intersection. If it's intersection, that's 1/2 multiply 1/2, right? But this is union. So union is like the probability of A1 subtract. So basically, it's the how to say that so this probability is the, oh wait a minute, this may not be a good example. Let me think about it. Okay, so because I'm thinking the right hand side is the sum and from 1 to 2 of probability of AN, right? So in this case, that's observing, I'm not conditioning, that's A1, 2. That's like, should I use half plus half here? This is the probability of first flip get this, first flip get this. But these are sequential, right? This is sequential for 2 flips. So maybe I have to think about the first flip. If A1 is H, A2 is E, still for the first flip, and they are disjoint, then the union will be okay. Maybe, yeah, I think I'm creating a dilemma here because I should actually consider both of them. There are 2 possible events, right? By the way, it's okay. Let's consider just flipping a coin once. and there are two destroying events. Either you land on head or tail, right? Then this makes more sense, right? Okay. Then this also is add up correctly, right? Because sorry, this is plus, this is 1, right? And then the union one here, you can see this is just the P omega basically, right? And this is also 1, right? So this two actually can establish equality. So this will hold. Okay, I think this is the one that makes sense. We consider the same random experiment, but the disjoint like outcomes, right? And this may be too special. Let's look at one more example. So let's say lower die, right? This may be give us more possibilities. So lower die maybe once. Then I consider some destroying events. A1 is equal to just get the outcome 1. A2 is the outcome 2. Let me create 3 of them. A3 is equal to outcome 3. Okay. Then the union I from 1 to 3 of AI, right? The union, joint union of this will be the, let's consider the probability, will be the probability that you land on either, so it's either 1 or you end on 2 or 3. And this probability is, as you can see, it's 1 over 6. 1 over 6, that's half, right? And then if you take individual probabilities, right, you end up at the same result, I believe, right? Sum I from 1 to 3 of 1 over 6, that's also half. So these two are equivalent, right? Okay, so you can see the probability is very intuitive also, right? So the probability of individual events, right, all this add up should equal to the probability of the destroying, like union of the destroying events, right? Using these two examples, you can see this is actually very natural, right? When I say unnatural, the only unnatural part is this should hold not just for finite, right, but just for all the countable units. Because for actual concrete examples, I cannot really give you an example of countable cases, right? Because I have to specify where I stop, right? I only have a finite number of events. But the definition, right? From the definition, this actually probability measure actually extends to countable units. Okay, so hopefully that can like help you understand, right? There's a relationship, right?
Much better.
Yeah. I mean, for flipping a coin and die, usually I use these two. They are simple. Now, yeah, I wanna start from here. So basically, I wanna do the basic properties. Let's see some basic properties of the probability measures. Let's give two of them here. So let's say I have consider two sets. A and B, they belongs to a sigma algebra. And also I put some like a restriction that A is a subset of B. Notice that this is an equality sign here, so it's not a proper subset. It's just okay. Then the probability that B difference A equal to the probability of B, subtract the probability of A. Okay, that's the first property. Second property, for any AB belonging to F with a subset of B, then PA less equal than PB, right? And P of A complement equal to 1 minus P of A, and P empty set equal to 0. Okay, so these are some of the property of a probability measure. So let's try to think about how should we make a simple proof for this, right? So I make A to be a subset of B because I want to make sure this thing is valid, right? Because if A is even larger than B, then B subtract A is not well defined, right? We cannot really define it, right? So it only holds when A is a subset of B. Other than that, this doesn't play a role, right, in this equality, right? Just to make sure this quantity is meaningful, right? That's the only purpose of imposing these conditions. Okay, so here the idea is that we have to utilize some property of the probability measure, right? Especially the second one, right? The union, the probability of the union is equal to the sum of the probability of individual items. But we have to make sure that they are like a totally like a mutually exclusive. So here we identify two mutually exclusive ones, right? So B subtract A, you treat it as a set. Certainly, this is an adjoint, right? Is disjoint. So disjoint. A, right? This is for sure because you take everything about B, subtract everything belongs to A. Certainly, you don't have any like intersection with A anymore, right? So that's okay. So if I draw a diagram here, A, B, right? So the B subtract A is just like B subtract A is like this, right? Maybe I'll make it bigger, but like this doesn't include this part. Okay, so that's disjoint from A. And also from this diagram, you also notice that B subtract A union A is equal to B, right? If you take the union of these two, it's equal to B. Now, I use the second property, right? Very simple, one line proof, right? So then you use the union, right? So the probability of B subtract A union A is equal to the probability of B subtract A plus the probability of A, right? And the left-hand side, this is equal to the probability of B. So you know the probability of B is equal to this plus this, and then you have proved this equality very easy. Okay, now the second one. So the proof of second item here. So if A, so this is meaningful then, right? So now if A is a subset of B, then B difference A is well defined. Then we also have the previous identity, right? Then we have this B difference A union A is equal to B, right? We have utilized this before. Then we know the probability of B is equal to the probability of B difference A union A, and from this countable union property, additivity property, we have the probability B difference A plus the probability of A, right? Now, this is well defined, right? For any well-defined probability, because the domain is 0 to 1, so this is bigger or equal than, that's what I have to say, bigger or equal than. Bigger or equal than 0 plus PA, right, which is equal to PA. So this means probability of B should be larger or equal to probability of A. So this, the first claim of the second item is proved. The second one, right? So we know A and AC are disjoint. And A union AC equal to omega, right? Then we have 1 will be equal to the probability of omega. That's the first probability of a probability measure, right? It's equal to A union AC. And then from the second property of the probability measure, this is equal to probability of A plus probability of AC. Then you rearrange, you get what you need, right? That's the, okay. That's the second claim. Oh. Okay, now I see everything. Now the third claim, even simpler, but because you have omega is disjoint with empty set, right? And omega union empty set is equal to omega, then probability of omega, which is 1, is equal to the probability of omega union empty set. From the second property is the probability of omega plus probability of empty set. Even from here, right, you cancel out this term. This implies that the probability of empty set is equal to 0. Okay, so this is a clear consequence of the first problem. Now we have proved the simple properties. Okay, one last thing is on the sigma algebra. So I have to give you some example of a sigma algebra. So let me put it on here. Sigma algebras. So let's say if I have a A, right? I'm talking about the sigma algebra A, right? So let's say I have a A that is a subset of omega, let's say. I use this notation. Sigma A denotes the sigma algebra on A or generated from A. And we can write it down. So sigma A will be equal to, first of all, in any sigma algebra, you have omega. You have phi, right? These are the basic building blocks. Now you know A, right? You are talking about sigma algebra generated by A, so A must be an element. If A is an element, A's complement is also an element. Yeah, that's it, right? Because now you can take union of phi and A, union of omega and A, and every operation. Then you can see you only have these 4 elements and no more, no less. Okay, just this 4. So that's the first example. Second example. Now let me give you what is omega. If omega is the lower die, right? So you have a collection of 1, 2, 3, 4, 5, 6. But that's omega. Oh yeah, and then you let the A to be a subset of it. So let A to be 1 and 2. That's a subset, right? Then what is the sigma algebra generated by A? Just from the previous example, right? That's just an illustration of the previous example. You have omega, you have phi, and you have A, 1 and 2. And you have A's complement, which is 3, 4, 5, 6. And that's it, right? So when you write down this, you have to be careful. The sigma algebra of a set is a set of set, which means you have 2 layers of curly brackets. You can see you have an outer layer of curly bracket, and inside here, this element, it also has a curly bracket because these elements are not scalars, right? These elements are actually sets themselves, right? So it's very important you don't forget about this inner, like the curly brackets, right, when you write down your answer. So here I'm just giving you some very, very simple examples. No? Okay, I think that serves the purpose of today's class. I think pretty much we have talked about, let's go back to the beginning point. So the purpose for today's class is to make you understand what is omega, what is F, what is P, right? Now, omega sample space, F sigma algebra, P is the probability measure, which satisfies 2 properties, P omega equal to 1, and also the countable additivity, right? The uncountable union of events, right? You assign the probability P of the countable unions of events is equal to the countable summation of the individual probabilities, right? Remember that. And also we learned some symbols, and I mean, there's quite a lot. I mean, especially for people who haven't like learned the probabilities so far. So yeah, there's quite a lot. So please review them. As I say, let me put it down here. You have to read please read chapter 1. Let's say also chapter 2 of the Law School and the textbook, FT, textbook. Very important, right? Don't just rely on the lecture, but read the textbook and try to utilize this to help you understand, right? Because the textbook is the most important one for you to understand the concepts. Okay, I think any questions so far?
Professor, can you hear me?
Yeah. Yes, I can hear you.
Okay, just one question on the textbook.
Sure.
You said earlier that you were going to provide a PDF version of the books, right?
Yeah, if you need I mean, you can search for yourself. I cannot, I mean, technically, I cannot provide a textbook on the Canvas. That's
Okay.
a violation. Right?
Oh, okay.
But you can search yourself, right? You can
Mhm.
find options from Amazon, the used books, right? Don't buy the new one. Used books should be, because it's 2014, right? It's 10 years ago, so it should be pretty cheap.
Okay,
And there are many versions. And if you really don't need my help, you can email me. I can see if I can share the textbook with you.
sure.
Okay.
Thank you so much.
So, okay, what I'm going to do here, okay, I'm going
I have
to
a question.
try forget. Yes.
Here, can you just draw a Venn diagram for the relation of B difference A union A equal B?
Which one?
So if you
The
go back one page. Yes, the last one. No,
here on the next page. Which one?
no, if you move forward, just move forward one slide. One more.
Yeah.
Uh,
Or you tell me
It's B difference A.
Okay. Let me use the last
A
page. Okay.
will
It's,
be. Yes.
bear with
yes,
me, okay.
correct,
You
the one
mean
before the last.
B difference A
And then between brackets,
there's a bracket and then
union A equal B.
equal B? I don't have this notation.
Union A.
Union R. You mean union R? I see. You want me
Probability.
to prove this, right? Okay.
Yeah, can we do a Venn diagram just to see that it's
Yeah. You can do my diagram. This is very easy to prove, right? I mean, just take this. Right? This is omega. You always draw omega. That's a rectangle. That's the universe, right? That's a sample space. And then you have A and B. Let's put it generally like this, right? Then B difference A. Let me use a color purple here. B difference A is take everything belongs to B but doesn't belong to A, right? And then A is A itself, right? So
Right.
A is A, and then I take the blue one. A is A. Now you take the union. You can see you add everything. Wait a minute. B difference A union A equal to B. Wait a minute. So maybe I got it wrong. So
It's in the previous slide. If you go back to the previous slide.
yeah, I know. I'm just trying to okay. Did I make some mistakes? So okay, B difference. Okay, let me just draw it. That's A and B here, right? And then B difference A. Did I understand it? It's just taking this part. Union A. It should be A union B, right? Maybe I make wrong. Yeah, you are right. So you mean here, right? Yeah, here, right? This one.
Yes.
Okay.
And on this,
Okay.
there's also, it was in red in the slide after this one. You put it in red as well.
Yeah. So let me see. Then, okay, you are right. So E of A union B. I see. There's a precondition. Okay. In general, this is not true, but okay, now I see. Because if A belongs to B, it's a subset of B.
Okay, so it could be on B. Okay.
Yeah. So in general, so I'm drawing the diagram in general, certainly that's not true. Okay. Now I see why I get this confusion. Okay. Now I have to put it down in this way. So I have to assume if A is a subset of B, then this is true. We put a precondition. Now let me show you the Venn diagram for this. So
Got it. Okay. So I shouldn't, I looked at
omega, just to be complete. Now I see. Okay, this is A. Then is okay, let me just do the purple one. Then the B difference A is the outside, like this bagel area, right? And now you put this union of A, you add this yellow part, right? So this purple add the yellow part is exactly B, right? So this is correct.
Okay.
Yeah, but there's a condition. You are right. We have to be careful. If A is totally a subset of B, then this will hold. Otherwise, I mean, in general, this is not hold. Yeah, that's right. Yeah. So this Venn diagram will help you understand this part.
That's clear. Thank you, Professor.
Yes, thank you for the question. Yeah, it's the clarification for illustrate. Yeah. Okay, so any other questions? So what I will do before I forget, I'm going to save the PDF of this whiteboard. It's here, so I'm going to label it. Today is September 9th. I have to upload this onto the Canvas, and yeah, that will be done. So yeah, so after I end this Zoom session, the recording will be available shortly, I think half an hour later. And yeah, I mean, I'm also holding office hour today, so yeah, in case you want to discuss or anything, you can come to the office hour. Yeah. Okay, so as I say, next week, my PhD student will take my role and give you some lectures, and yeah, he will also do the same using this whiteboard and upload everything. Okay, so I will stop sharing now. So, okay, so thank you, everybody. So I think I will see you in 2 weeks. I mean, but next week we still have the class. Don't forget to come to the class. Okay, I will post the assignment maybe week 2. I will give you some assignment 1 to work on. Okay, thank you, everybody. I will end the class and yeah, and the Zoom class now. Okay, bye.